Okay, so can you see
Yes, sir.
this? Yeah?
Yes, sir. Visible.
Okay. All right. Let me just go to the slideshow mode. Yeah, is that clear
Yeah,
now,
perfect.
slideshow?
Perfectly, sir.
Okay, all right. So again, thank you so much for the opportunity today to present some of our work that we're doing at Nottingham and kind of around the world in terms of the state of the art on how we can engineer bitumen, which is the major thing that we use to make our roads, and roads are one of the most important one of the most important national assets, right? When we consider our future of our country, as well as things like how we can engineer better roads and more resilient roads, and so on. So yeah, so I'm Anand. I'm currently a assistant professor at the University of Nottingham. Yeah, we have a very big sort of transportation engineering center that we call as the Nottingham Transportation Engineering Center. So before I begin my presentation, I'll just talk a little bit about pavement engineering research at Nottingham, and what we've been doing over the past and what are our current areas of research in terms of meeting the big challenges that we face for our infrastructure as well as for our road network. So pavement engineering research is not new to Nottingham. I mean, it's one of the, I think, if you look at the two main centers for pavement as well as highway engineering research, there was one in Nottingham and the other one was at Berkeley in the United States. So these were the earliest centers for pavement engineering. So pavement engineering research has been undertaken in Nottingham since about 1950, so about 70 years from now. From today, that is. Initially, it was started under the leadership of two sort of eminent professors, Professor Peter Pell and Professor Stephen Brown, and it was combined with geotechnical engineering because that was how pavement engineering was seen at the time, that it was an extension of geotech. Over time, the importance of pavement as a national asset came to the forefront, and there's been more and more research that's being done in pavements. We formed the Nottingham Centre for Pavement Engineering around 2001, and then we also sort of extended into new areas, and we also changed our name to what we call today as the Nottingham Transportation Engineering Centre. I think even now, I have a lot of colleagues and friends in India, and I think this area of research is absolutely booming at the moment. Nearly all the national institutes in India currently have active research programs in pavements because it is seen as a sort of a very important area when considering the development of the country and so forth. Yeah, we are quite unique in the sense that we have quite established laboratories for pavement engineering. So this building that you see here is what we call as the pavement engineering building. We have dedicated laboratories as well as technicians that look at all aspects of the design, testing, as well as the monitoring of pavements. So our main research themes is primarily in the design and performance of pavements. How can we design pavement materials, prototypes, laboratory tests, frameworks to ensure the long-lasting or the resilience of our transportation infrastructure. We also do a lot of work now on sustainability, so the development of technologies and decision frameworks aiming at facilitating the implementation of different kinds of things that are currently important, such as the circular economy, carbon reduction, sustainability principles in transportation infrastructure engineering. Other aspects that we're currently looking at is resilience. I mean, this is now becoming a very important topic. What exactly is resilience when considering infrastructure and especially for us, road infrastructures? How can we define materials, frameworks, and technologies to design, construct, and maintain our road infrastructure and to adapt to progressive change? And what we're seeing more and more is absolutely the emergence of extreme events and how we can engineer our infrastructure to meet these demands of these extreme events. Some of the other areas that we're also looking at, these are more new areas of smart systems, performing sort of multidisciplinary fundamental and applied research with the aim of developing new materials, technologies, decision framework, next generation of smart transport infrastructure. So we have three academics at the moment that are looking at things like Professor Gordon Airy. I mean, Gordon Airy, if you've been working in payment and highway engineering, you would have come across his name. He's a sort of an authority figure in our field. So Professor Airy's research mainly looking at things like rheological testing of bitumen, bitumen filler mastics, durability, use of secondary recycled materials, bitumen modification, alternative biogenic binders, and so on. So, and he's had a career of more than 30 years in this field. So he's done numerous international as well as national projects related to payment and highway engineering. Another academic we have is Dr. Nick Thom. I mean, if you've studied payment engineering, you probably read his book. So he's the author of the Introduction to Payment Engineering book, which has about 3 or 4 volumes now. So Nick is actually from industry, but now he's an academic, and he works on all main aspects of payment engineering, such as prediction of payment as well as railway when looking at many things like ballast and so on, damage mechanisms, tire payment contact, skid resistance, monitoring and evaluation of payment deterioration, and so on. So the last academic is me. I've been in Nottingham for about this is my second year. So previously I was at the University of Cambridge. I also have experiences in the University of Texas and also in the University of Hong Kong Polytechnic. Very small scale, and trying to understand the nature as well as the chemistry of these materials to see why they behave in this way on a more sort of macro scale. So my research looks at things like advanced material characterization, road material recycling, circular economy, smart payments, and so on. So that was just a sort of a brief introduction to to Nottingham, our research program in Nottingham, and what are the main areas that we are working on. So hopefully, over the course of the next, I guess it's quite late in the day already in India. I think it's almost about 5:30. So I mean, hopefully, I will keep you engaged for a little bit. So I'm mainly going to talk about what are the recent advancements that we are seeing in terms of payment materials, and how we can engineer payment materials to be more conducive to the challenges that we face in the future. So that's the main idea behind this presentation. So hopefully, it's interesting for you, and you can take some ideas that will help your own research and study. And I'm very happy to answer any questions either after this presentation, or you can anytime send me an email and we can have a chat. All right, so when we look at advancement of payment materials, I mean, we are seeing, this is an area of active research. There's a lot of news when looking at pavements, bitumen, roads, things like that. People are talking about, can we make payments more smarter? Can we add different things such as plastics, maybe some anti-aging additives, recycled materials to make it more sustainable? And why we need to do that is that when we sort of project into the future, we need our infrastructure to be more resilient. We need our infrastructure to be more resilient to climate change, extreme events, and so on. We need our infrastructure to be smarter in the sense that we're going to have autonomous vehicles, we're going to have platoons of cars, and so on. So can we make our infrastructure smarter so that we can deal with all of these things? We need to make it more sustainable. We also need to make it more engineered for performance. So this is where we need to get to. However, the only way we can get to this as business as usual, we cannot meet these demands for our future paving materials as well as our road infrastructure. But the only way we can do that is by innovating. And the two main areas we need to innovate is in terms of our material understanding. So bitumen, which is the black kind of gooey substance, I think everybody has come across it. Maybe you've never felt it, but you've definitely seen what bitumen is and what asphalt is, because it's everywhere around us, right? All our roads are made of asphalt. So it's a very, very complex material. It's a material that is made of millions of different organic compounds. It's quite similar to the human body, because bitumen comes from the so bitumen is a highly complex material. So to understand these materials better, we need more innovation in terms of our material characterization, as well as we need better selection. So if I could know, okay, this type of bitumen is going to work well in this weather, this kind of bitumen is going to last longer, then I can make better selections when thinking about the future challenges that we face. I like to show this slide because yeah, it really kind of puts into place what engineers think was the petroleum chemist thing. So for a highway engineer, bitumen is a substance that causes particles of sand, gravel, and crushed stone to basically, bitumen is a residue of petroleum or a product of solvent extraction of petroleum. It is a complex mixture of thousands of different organic compounds mutually dissolved or dispersed. So as a researcher, we work at the interface of this. We need to understand what our material is. It could be bitumen, it could be concrete, it could be aggregate. But we also have to think about what is the end application. So I like to show this slide because to show this is where, this is my perspective. I work at the interface of this. I understand what the material is, but on the other hand, I also think about, what is the end use, right? Because, it's not enough to just get bundled up in the science. We have to think about how we can engineer these materials to make it better. Yeah, so this is a sort of the UK has a net zero roadmap. I'm sure there are similar things in India and other countries of the world. Over 96% of our road network in the UK is surfaced with asphalt. I think it's similar numbers in India, making it one of our most widely used materials and one of the largest sources of carbon emissions. So there is sort of two main plans, which is mainly looking at things like material decarbonization, material resilience, and so on. However, from the more kind of material perspective, the two main things that we're looking at in terms of decarbonization is in terms of durability. Can we make our materials last longer, more resilient? And secondly, in terms of recycling. So these are the two main plans that the UK highway authorities, but I believe it is similar everywhere in the world, is to look at how we can reach some of our demands that I shared in the previous slide. So one is looking at durability, and the other one is looking at recycling. So, this is kind of the waste hierarchy which has been established by the European Commission. So when we look at any material, so there are many ways we can look at the end of the life of a material. So one of the, the easiest way to do it is we just dispose it, right? We just throw it away. The more sustainable way is to look at some other recovery methods, maybe energy recovery and so on. An even more sustainable way is to recycle the material itself. The second most sustainable way is to reuse the material. So if you have a material, it's come to its end of service life, we reuse it. And the most sustainable way actually is to prevent the damage in the first place. So this is an interesting point in my opinion, because as a community, when we talk about construction materials, we are always obsessed with recycling. We want to recycle. But actually, the best way, the most sustainable way, is to extend its service life, right? To stop it from damaging. That is essentially the most sustainable way. And what that means in terms of road infrastructure is that it means in terms of durability, right? Can we increase the durability of our road materials so that it can last longer? By lasting longer, it is more resilient and it is more sustainable. So to do that, for bitumen, bitumen mainly deteriorates because of this thing, as we call as aging, which is the oxidation of bitumen. It makes it more brittle. It leads to fatigue cracking and so on. So we need to understand the phenomenon of aging, and can we look at things like anti-aging to prevent it from deteriorating in the same rate? And also, can we engineer better materials so that it lasts longer, so that it is more durable? So these are some of the things that I'm going to talk about in the next slides. Okay, so in terms of the circularity of pavements, there are different types of approaches that have been developed. In the UK, we have developed a sort of a framework that we call as the integrative approach towards maximizing material circularity. So the four main things that we need to do to increase the material circularity is to look at the high value material use, which is essentially like, for example, if we recycle our materials, can we keep its original value and not downcycle it? And there's more sort of, kind of other elements that are involved in looking at things like material flows, material passports to increase the circularity, things like, adaptations to processing and production technologies to maximize circularity. And lastly, looking at things like performance as well as the environmental hazards with increasing circularity. So my main research is to look at this number one, which is the high value material use. So can we understand the material to such a detail that we can keep its value as we go through different kinds of life cycles and so on? And also, can we engineer these materials to be more durable so that essentially they last longer? And by lasting longer, it's a more sustainable approach to our managing our road infrastructure. Okay, so when we talk about bitumen deterioration or pavement deterioration, one of the most important factors that we need to think about is bitumen aging. So, so what is bitumen aging in terms of chemistry? So bitumen aging is believed to be the aggregate of the oxidation reactions and polymerization, as well as the evaporation of the lighter components of bitumen to a lesser extent. That's the chemical definition of bitumen aging. What does that mean in terms of engineering? Is that bitumen aging leads to the hardening of the material and loss of its performance. So essentially, bitumen is it's a viscoelastic material. It has some element of elasticity, and that's what gives it its good properties as a paving material, right? So that because it can relax when stresses are laid upon it. However, when oxidation happens, you have oxygen enters these molecules, they make it more and more stiff. And as a stiff material, it is more brittle, it's more prone to cracking, both in terms of the fatigue cracking, long-term cracking, as well as low temperature cracking. So the reasons our pavement deteriorates over time is mainly because our material, the original material, is not good anymore. So and it's weak and it's more brittle. So again, I like to use analogies. One of the main analogies I like to think about is also like humans, right? As we age, we become more stiff. Our body starts to ache over time. Our organ starts to fail. So if there was any way we could keep ourselves younger, we would try to do it, right? That's what we try to do in terms of, we do exercise, we do different things. So similarly to that is the same idea here. Can we understand the aging process of bitumen, and ultimately can we prevent this aging from happening, or at least reduce the rate of aging? So I hope that's something that's understandable. So yeah, again, bitumen aging, I just want to stress the point here, oxidation is of significant importance to pavement researchers and engineers. Oxidation leads to the increase in stiffness, increase in the tensile strength, decrease in the ability to relax, and embrittlement of the binder. So what that means is that in terms of chemistry, oxidation is the introduction of oxygen-containing functionalities on molecules, which increases polarity and really immobilizes an excess number of different molecules through intermolecular association. So that's what happens in terms of science. What really happens in terms of physical properties is that it gets more stiff. And once it's stiff, it's not as good as the material anymore. So yeah, so if you think about it, the bitumen aging has been a focus of studies for a long time, because it's just what leads to, it is one of the main factors that leads to the pavement failure, right? So people have been looking at aging from the 60s onwards. So things looking at the kinetics and impact of aging. So this is understanding how fast or slow aging happens. Simulating aging in the lab. So can we simulate how aging happens in the lab so that we can understand aging and also design better materials? So that's another area of research that's been going on. And one of the main factors in that is that understanding these two things, how fast aging happens and simulating aging in the lab, it helps us to improve our performance prediction. So we can think about how our pavements would perform by understanding the aging factors, right? And the other factor is the research that has been going on since the 90s, is that looking at the addition of antioxidants. So antioxidants are basically kind of additives that we can add into bitumen so that it reduces the rate of oxidation. So these are the two main factors that have been considered when looking at things about the aging of bitumen. So I'm going to talk a little bit about those things in the next slides. Okay, so So when we look at the history of aging, there's been major developments happening since the 70s and 80s. There's been sort of landmark works on aging by Peterson and so on. So if you're quite familiar with pavement engineering and bitumen engineering, you would have come across these papers. However, since then, since the 80s, we've only kind of made very incremental advancements. We have not really made any major advancements, and that's what I'm going to talk to you about today. And one of the main reasons for that is that we've stick to some kind of traditional methods of characterization, such as infrared spectroscopy and so on. However, there's a big need for different kinds of bold as well as innovative ideas to transform the understanding of aging, and that's what we're going to share some slides on one study that we did in that aspect. So one of the ways we can really understand the sort of the intricacies of aging is to use very, very advanced spectroscopical tools. In this case, the spectroscopical tool that we used was something called the Vocus proton transfer reaction mass spectrometer. So the proton transfer reaction mass spectrometer is something that we can use to fingerprint volatile compounds and detect the real-time oxidation characteristics of different materials. There are newer versions of this PTRMS, as we call it, with drastically enhanced sensitivities and enable the detection of a vast number of semi-volatile as well as low volatility VOCs and their oxidation products. One of the major kind of unique characteristics of this kind of device is that it has the range of identifying different molecules in terms of the parts per trillion. So newer models of these spectrometers they have very, very high resolution. So you can really understand the exact chemical nature of these materials, and understanding these exact chemical nature of these materials will allow us to understand the oxidation process. And understanding the oxidation process will help us to develop better materials. So I hope that kind of, I don't know if all of you are from this particular field, but I hope that kind of that logic of why we do things is clear, because I'm sure this is also applicable to some of your kind of work as well as your studies. So in terms of the scope of this study, so we looked at the use of Vocus spectrometer as a tool to chemically fingerprint asphalt binders at a very high time and chemical resolutions. We looked at things like the real-time observation of rapid changes in the chemistry of different asphalt binders during oxidation. And we used 3 different asphalt binders or bitumens to examine the sensitivity of this technique. And we also use different kinds of air blankets that have different oxidation potential. For example, nitrogen, nitrogen has almost 0 oxidation potential, right? Because it doesn't have oxygen. Air, which has some oxidation potential because our air is made up of around 20% of oxygen, isn't it? And ozone enriched air. So ozone is a very, very potent oxidant. So it can increase the rate of oxidation. So this helps us in kind of a laboratory setting where we want to accelerate how fast or slow oxidation happens. And then one of the kind of the main sort of caveats in these techniques is that because these instruments are so sophisticated, they give us a huge amount of data, and to process this data, it's not easy. We have to use some kind of data mining as well as sort of machine learning techniques and statistical techniques such as hierarchical clustering, factor analysis, and so on. So this is a little bit about the experimental setup. I'm not going to talk much about it. I think the key point is that we get a lot of data from these instruments. And again, to manipulate this data, we have to use some kind of advanced data analysis techniques and so forth. Some of the results, we could see by studying these asphalt binders. So just want to say that I use asphalt binder and bitumen interchangeably, right? Because bitumen is what really binds the asphalt. So, another word for bitumen is asphalt binder, but I will try to use bitumen. So in terms of bitumen fingerprinting, we could see that the chemical compositions of bitumen samples showed very extremely complex emission profiles with the complexity rising as a function of temperature. We were able to observe a number of sort of low volatility compounds such as multi-oxygen compounds, that is a number with oxygen atoms more than 5, which shows that the instrument was kind of sufficiently sensitive to observe different kinds of trace level concentrations of some extremely low volatility compounds. And again, we embrace this complexity by applying different kinds of multivariate methods to study the emission profiles of these kind of bitumens in terms of the entire mass spectrum. One of the ways we did that is something that we call as hierarchical clustering. So this method allowed us to visualize the different kind of taxonomical relationship between the binders. We were able to kind of visualize cluster heat maps, which kind of shows the magnitude of chemical expressions in the different compounds. So for example, the x-axis here are different kinds of chemical compounds in the bitumen, and the color essentially shows the magnitude of the expression of different types of these molecules. So when we have 3 different samples, we could see that the molecules are expressed differently. Whereas when we had also 3 different air blankets, we could see that the different kinds of air blankets have different oxidation potential. So overall, this method illustrated that the effectiveness of the analytical approach in distinguishing the degree of chemical expression of different compounds among the 3 different binders. So what is the key point here? The key point here is that as we add more and more binders into this kind of clustergram, as we call it, different distinguishing features unique to different binders can be observed. So compound-specific differences represented by color as well as the hierarchical differences. So such similarities or dissimilarities, when quantified over a larger pool of more diverse binders, it can really help explain the observed differences among different binders in terms of their oxidation rates, effectiveness of different additives, modifiers, and other chemomechanical features. So this thing, what we call here is, we call it as the bitumen fingerprint. So, using this, we can really fingerprint the exact chemistry of this material and so on. So these ideas mainly come from bioinformatics. So, if you look at bioinformatic research, you can often find these kind of diagrams, which is used to show the expression of DNA of humans or animals and so on. So, and we use the same idea to understand the exact kind of the chemical nature of these materials in terms of their chemical compounds and so on. So this is something that we did a few years ago. Another way we looked at analyzing the data, we used techniques kind of like called factor analysis. So factor analysis is it's a well-known multivariate method that can be used to reduce data from a substantial quantity of observed variables to some fewer observable variables. So using this, we were able to see how these factors could be divided into common themes. So some of the factors that we could see was that the oxidation reaction products reduce aliphatic molecules, reduce aromatic and unsaturated fatty molecules, and so on. And these interpretations, they mainly relied on different kinds of time-dependent behavior and the presence of characteristic kind of marker molecules in each factor. So some of the key sort of takeaways from the factor analysis was that we could see that the top molecules in the oxidation-related factor, it showed a number of highly oxidated organic molecules. Such highly oxygenated molecules could be formed sort of via multi-step auto-oxidation processes involving the initial peroxy radicals. So we looked at this in more and more detail, and we could find interesting kind of information regarding the asphalt binder oxidation mechanisms. So the key point here was that using such kind of advanced spectroscopical tools, we were able to see evidence that was only before it was simply postulated based on some kind of theory. So here we were able to provide experimental evidence that supported some of the classical kind of oxidation mechanisms, which basically said that different kinds of carbons, in this case benzylic carbons, would dominate the possible initial oxidation pathways. So this is something that we were able to do, and the idea here is that the more advanced kind of tools we can bring in to understand the nature of our infrastructure materials, we can really find out exactly what is happening in these materials when different kinds of deterioration process happens. So understanding these mechanisms, can ultimately be used to engineer kind of tailored solutions to mitigate oxidation process, in what would really be a sort of paradigm shifting approach to designing pavements, right? So that is just one part of the puzzle, is really understanding what oxidation is. But the more kind of the active approach is that, can we reduce the rate of oxidation, or can we prevent oxidation from happening itself? So if you prevent oxidation from happening, we can extend the service life of pavements, we can make it more sustainable and more resilient. So one way we can do that is by adding kind of specific kind of additives in what we call as antioxidants. So this would be a more kind of an active approach to mitigate oxidation. So the interesting question is, why have we not really focused on antioxidants? I mean, this seems like a more logical approach, right? Just like, as humans, to stop aging, we do a lot of things, right? We do some exercise, we apply some kind of creams and so on. So the reason we do that is we want to stop our bodies from aging. So similarly, we can also do the same thing with our infrastructure materials, is that we can, add certain additives to reduce the rate of oxidation, or maybe even preventing it. So there are two main approaches we can take, which is what I shared before. One is the mechanistic approach, which is understanding the mechanism, finding agents that prevent oxidation, and so on. And the other approach is the empirical approach, which is to identify the kind of best candidates based on current knowledge, and then we can cast a wide net to examine the efficacy of these different materials. So to do that, we formed a sort of a global consortium. We formed a global consortium of different research centers around the world that is looking into this kind of research. I think we've got a couple of universities in India, IIT Kanpur, as well as IIT BHU. They're also part of this consortium. So as a consortium, we're doing kind of research to understand what are the specific antioxidants that we can add to reduce the rate of oxidation. So in the first phase of the consortium, we looked at 4 specific additives, things like lignin, calcium hydroxide, zinc, phenothiazine, and then we conducted a round robin sort of laboratory testing, and then we were able to see sort of promising results. And in the part 2 of the consortium, we had about 27 different bitumens, 2 antioxidants that we looked at, things like zinc as well as craft lignin, and we had about 16 different labs that participated around the world in this effort. And we were able to see sort of key results from this was that we could see the positive effect of lignin, which is it's an antioxidant additive that we added, and we could see the remarkable effect of ZDC, which is a zinc-based additive, in reduce the stiffening or reducing the rate of oxidation. We could see that the zinc showed reduction at different dosages, as well as at 3% as well as 5%, and we could also see that the stiffening index, or the rate of change of stiffening, which is an indirect measure for oxidation, was around 50% lower when we added these specific antioxidants. So what are the key takeaways from this approach is that, the physicochemical processes that govern antioxidant behavior, it is very complex, right? We still don't really understand it, but we need to understand it to make more durable mixes in the future. Understanding the rheology is important. The reduction of oxidation is simply a precursor driving mechanism. So the ultimate kind of change is a rheological behavior. Zinc is a really promising additive that we want to investigate more, and it seems to show effectiveness for most bitumen materials. However, the sort of caveat here to remember is that we still observed considerable anomalies looking at the results. So although these additives seem to work for most bitumens, it does not seem to work for all bitumens. So that's something, again, that we have to think about and investigate, is that what is in the specific chemistry of different bitumens that make them more effective and less effective in terms of modification, as well as the addition of antioxidant additives and so on. The other way to look at it is to we can understand bitumen mechanisms, how they happen. We can also look at how to prevent it. But we also need to kind of simulate bitumen in the lab, right? We need to simulate how aging happens in the lab, because that will help us to understand how a specific asphalt mixture is going to behave over time. Yeah, because asphalt mixes and pavements are designed for 10 years or 20 years. We cannot wait 20 years to see how our material will behave, right? We need to understand today how our material is going to behave 20 years in the future. And one of the ways we can do that is that we can simulate aging in the lab. And different people have developed different methods. So one of the main common method is from the US. It reported that we can age loose asphalt mixtures at 95 degrees for about 5 to 6 days in a laboratory. And this would be the way to simulate how these materials degrade over maybe 10 years. However, still, the 4 to 6 days is still kind of undesirable and impractical for routine testing. So we did some work on how we can reduce that 4 to 6 days to even lesser than that of using just one day. So the way we did that is, we developed what we call as the ozone-based aging method. So ozone is a very powerful oxidant. So, if we can use ozone gas to increase the rate of oxidation, we can simulate, how oxidation might happen over 10, 15 years very, very quickly in a laboratory environment. So there's a few ways we can increase the rate of oxidation. One is to increase the temperature and thereby increase the rate of oxidation. We can also pressurize the specimen, which is basically the same as increasing the temperature. Or we can also introduce kind of highly oxidative species into the aging environment. That is what we did in this. Then the aging of the loose mixtures in an enclosed and heated tank, and lastly, the degradation of the oxidative gas. So this was essentially based on what we call as the Viennese binder aging method. We used oxidation. We used air, and then we used an kind of ozone generator to produce what we call as a reactive oxidation species. So these reactive oxidation species really help to increase the rate of oxidation, and that's what we saw in this study. So how did we compare the effectiveness of this approach? We did the 1 day of what we call as ozone aging, and we compared it to the 5-day oven aging, which is what is traditionally done. And we compared its effectiveness in terms of meeting different kind of rheological as well as chemical parameters. So one of the ways we did that is we aged our samples in the ozone for 1 day. We aged some samples in the oven for 5 days. After the aging process, we recovered the binders using the solvent extraction, and then we characterized it for rheology using a dynamic shear rheometer. So these results were calculated based on some very basic parameters such as the G star sine delta parameter. And we could see that the binders aged using the ozone method showed higher PG grade, meaning they were more stiff and meaning they were actually more aged, right? So this method really showed that the effectiveness of this method to accelerate oxidative aging. So the level of oxidation and kinetics of aging exhibited by the binders, they're a function of different factors such as sulfur content, availability of oxygen and diffusion, and so on. And the same binder can show different quantitative levels based on these indices when exposed to different kinds of experimental conditions. So overall we could see that both based on the infrared spectroscopy results as well as the rheological characteristic results, that using highly potent oxidative gases and developing a method around that, we can increase the rate of oxidation. So although our laboratory simulation of oxidation maybe 5 days, 6 days, we can reduce that to even lesser time, such as 1 day and so on. So this was some of the work that we did on oxidation. If anybody's interested to know more, I think it's a lot of content that I've covered. I'm happy to share some of my papers, or to have an alternate discussion with any of you. So yeah, in the last part of this presentation, I'll talk a little bit about bitumen as a material and how we can modify bitumen with different kinds of additives, plastics, rejuvenators, and so on. One of the ways that we've been working here in Nottingham is to understand bitumen at a very fundamental level and using what we call as the solubility parameters. So using solubility as a scientific approach towards kind of bitumen modification. So when we talk about bitumen modification, these days there's a lot of research. People are adding all kinds of things into bitumen, right? It's very common to add plastics, kinds of waste, all of that. But is this really a scientific approach? Can X and Y be added together and perform as a engineering material if they're not compatible with each other? Can we understand compatibility at a very fundamental level, which we've been trying to do using what we call as the solubility parameters. So what solubility parameters helps us to do is that it allows us to do the physicochemical modeling of bitumen using kind of intermolecular interactions, and it provides fundamental insight into the nature of these materials. An interesting way to think about solubility is that if you have water and oil, they don't really like each other, right? So they will have very different kind of solubility parameters. But whereas if you have, I don't know, water and Coca-Cola, they will still mix together because they have similar kind of solubility properties. And that's what the same idea, we want to bring that to bitumen and as well as modifying bitumen. Yeah, so how do we develop kind of solubility-based model for bitumen? I mean, there are different kinds of approaches. We use the Hansen model, which is based on the method of turbimetric titrations, and it evaluates the physicochemical compatibility of bitumen in terms of different kinds of forces, such as dispersive forces, hydrogen bonding forces, polar forces, and so on. And we can model the solubility of any material, and a material like bitumen as a sphere, as a three-dimensional sphere. So it's very, very, very kind of a nice way to model the solubility of different materials. We can also look at the extent of different kinds of intermolecular interactions, such as what happens when aging happens. So when aging happens, the polar forces inside bitumen becomes larger because you have more oxygen, right? Oxygen is a highly polar material, and we can kind of quantify that semi-quantitatively when comparing different bitumen. So we could see that the age binders have more polarity, perhaps more hydrogen bonding, and so forth. But I think the real kind of beauty of this is of this model is we can extend it to different kinds of extenders, such as plastics, SBS, low density polyethylene, and so on. So the way we can do that is that we can model the solubility of bitumen as a sphere, and also we can model the solubility of the additive. So for example, SBS, which is styrene, butadiene, styrene, it is a very well-known modifier for bitumen, and it performs very well. And the reason it does that is because bitumen and SBS have very kind of similar solubility parameters. So bitumen and SBS, they really like each other, and then therefore SBS can behave as a added function to bitumen, even giving it more properties such as increased rutting resistance, increased fatigue resistance, and so on. Whereas if we add other kind of additives, for example, it's very common to add different kind of plastics into bitumen. You can see although the solubility sphere of the plastic is inside bitumen, it's very small, and it doesn't really have affinity to bitumen, and that's why a lot of the performance properties of bitumen may be compromised if we add different kinds of plastics, in terms of we have increased hardening, which will most likely lead to significantly deteriorative performance in terms of fatigue and low temperature cracking, and so on. So we've used it as a fundamental metric to see what kind of materials we can add and not add to bitumen. Yeah, recently we also extended this to different kinds of biomaterials. So nowadays it's very common to have what we call as the biobitumen, which is adding different kinds of biomaterials to bitumen and seeing and making it more sustainable. So, but what is the real kind of chemical process that happens? I mean, one of the way to look at it is that we can model this in terms of solubility. So, I mean, here this is just a graph of how we model the building blocks of bitumen, which is mainly the asphaltene and maltene within the kind of the solubility parameter. Yeah, and we could see that some of these bioadditives. Here we use two different kinds of bioadditive. The bioadditives that are most efficient, or the most compatible with bitumen, are the ones that have closer or more common solubility properties with bitumen, as opposed to the bioadditives that does not. So using these kind of models, we get a real kind of fundamental insight into what happens when we modify bitumen. And when we think of modification, this is a very important thing in the future, right? Like, our materials are going to be modified because we have to meet the demands of the future in terms of sustainability, in terms of increased traffic, in terms of increased resilience. But what are the best materials to modify it? One of the ways we can do that is by really understanding the nature of our materials at a material science level, instead of just focusing on the practice, which may lead to kind of more negative performance in terms of long-term goals and so on. Yeah, I think the last part of this presentation, I'm just going to talk a little bit about rejuvenation. So, rejuvenation is sort of the last part of the puzzle, right? So if we cannot extending the service life of our roads, our infrastructure, the best possible way. The second possible way is to look at recycling. And when we talk about asphalt recycling, I mean, we recycle asphalt because our material is not good anymore and has become more stiff and has become more brittle. So to recycle these materials, we have to add sort of things that we call as rejuvenators, right? Which basically give its good properties back. So I'll talk a little bit about rejuvenation and some of the work that we've been doing in terms of rejuvenation. So, it's very common to use rejuvenators to recycle asphalt. Here we just had about, I mean, we've been working with I think about 6 different rejuvenators commercially available, and seeing how we can kind of best optimize the process when it comes to rejuvenation. Yeah, one of the ways we can do that is to optimize the dosage of rejuvenators. I mean, so when we talk about dosage optimization of rejuvenators, again, we have to think about how we can balance the properties in terms of the rutting, which is the high temperature properties, as well as the fatigue, as well as the low temperature properties. And it's quite a challenge. I mean, it's a real engineering kind of design problem to balance these properties. The way we did it is by, we looked at things like master curves of bitumen, looking at things like how we can reach the original master curves of bitumen in terms of the unrejuvenated mixes. And this is some of the work that we did. If anybody's interested to look at some of the mathematics as well as how we did it, you can refer to this paper. So yeah, so the master curves were used to look at developing optimal dosage characteristics for the rejuvenator. So based on drawing master curves of the virgin binder as well as a rejuvenated binder, we can look at what is the optimal percentage that we need to add to balance the different kinds of properties that we need to look at. Because we don't want to simply make it excessively soft, right? We don't want our rejuvenated materials to be excessively soft. Sure, it can meet the low temperatures as well as fatigue performance, but then we compromise the rutting performance and so on. Yeah, so some of the main results that we saw is that by developing these kind of rejuvenation-based indices, we can linearly kind of correlate this with dosage and so on. And then using that, we can back calculate to determine the optimal dosage. And we can determine the optimal dosage just based on only 2 trials. So having, mixing, having a high percentage of modification and a low percentage of modification, and then using sort of a fitting algorithm, we can find what is our optimum percentage that we need to modify our materials. Yeah, so that's what I've talked about here. Yeah, so we try to manage the high temperature performance, we try to manage the low temperature performance, and then we try to optimize these dosages. So the optimal dosage is often, it's closer to the lower limit, which suggests that our approach of this kind of fitting algorithm-based approach, and it can also save the quantity of rejuvenators, right? And also leave some sufficient leeway for accommodating for the uncertainties and so on. Yeah, so the last part of this presentation, yeah, I mean, so when we talk about recycling, the other concept to remember is that the recycling is not just a one-off, right? When we think about the future, it's simply not just recycling one time. We have to think about how we can be recycled again and again and again. So we did some work on that as well, looking at multiple cycles of rejuvenation, not just one time, keep rejuvenating and seeing what happens. What we could see is that when we add these rejuvenators and we recycle again and again, we are able to meet some of the characteristics. So we are able to meet the specifications in terms of the high temperature performance. We are able to reach the specification in terms of low temperature performance. However, when we look more closely at the parameters, so there's a parameter that we call as the delta T of C, which is mainly the difference between the critical temperatures for low temperature in terms of the stiffness as well as the M value based on BBR results. Essentially, what delta T of C tells us is that although we are able to meet the low temperature performance in terms of stiffness per se, but we cannot, the rate of change of stiffness is not the same when we keep recycling it. So that means there is something happening in the material. Although we are able to rejuvenate it and meet some of the characteristics, it is still not the same as our original material. There is something that has changed in the fundamental chemical nature of this material that has still not become the same when we recycle it. And one of the main reasons that we think that's the case is that something's changed in the chemistry, and we still need to figure out why. And we have to meet that demand. That's the only way we can think about multiple cycles of rejuvenation, because the rate of change of stiffness is very important. Because when we look at things like low temperature cracking and so on, yes, it's fine if our material is not stiff, but the rate of change of stiffness is also very important in terms of looking at cracking and so on. So this is some work that we are currently doing, looking at multiple rejuvenation cycles, and can we engineer our materials to meet the demands of those kind of multiple cycles of rejuvenation. Oh yeah, so that was the my last slide actually. So lastly is just it's just a welcome to all of you. I mean, if anybody of you is interested to visit us at the University of Nottingham, if you are interested to collaborate with us, if you're interested to know more about our research, or if you're just curious about what we're doing, then please feel free to reach out. So you can join us at we also kind of recruit people in terms of PhDs, postdocs, as well as visiting scholars from India. We're happy to host any of you. And I think this was just a sort of an insight into some of the work that we've been doing. Hopefully, it has been useful for you. And I mean, I'm open to any kind of discussion, or if you have any questions, feel free to reach out. Thank you. Yeah.
Thank you, sir, for that fascinating glimpse into the future of payment engineering. Your presentation on the engineering bitumen to meet the transportation demand of the future has been truly eye-opening and inspiring. Sir, we have few questions. The participant have posted few questions in the WhatsApp group, and I have reposted in this chat. So we are taking the very first question. This is uh, what type of plastic cannot be used with bitumen? Basically, sir, most of the students nowadays, even in the MTech and BTech, are using like how to use the waste, basically the plastic in the bitumen, and then they redesign the pavement layers and all. So I think the question lies in that field only. What type of plastic cannot be used with bitumen, and how much life of the emulsion get reduced if we use waste like all type of plastic? Yes, sir.
So that's a very good question. So I think hopefully from my presentation you got an insight into so there's two separate things that's happening. So one is what type of plastic can we use and what type of plastic can we not use. So in terms of if we test it in terms of just mixing it in the lab and testing it in terms of some basic properties, then all plastics can be used, right? But what we need to think about is that, is this really a scientific approach? Is this really what is going to lead to a long-term performance? And probably you will see that that is not the case. So to answer that question, to put it simply, yes, in the lab setting, we can, obviously we can mix different plastics and we do some testing, we may get a positive result, but we need to look at fundamentally, are these plastics really compatible to be mixed with our paving materials? So that's what we need to look at. And to give a more kind of scientific answer is that, many of these plastics, they are plastomers, right? They are plastomers, like low density polyethylene, all of that. So when you add a plastomer into a bitumen, you will increase its stiffness, yes, but then you also create a lot of other issues in terms of the phase separation, in terms of the low temperature properties, in terms of the fatigue cracking resistance, and so on. So it's a very difficult question to answer, because I know that in India that people are using this quite a lot. But my suggestion to the students who are working on this is that yes, you can use it, but think of it in a more scientific sense. Like, try to go deeper into what is happening inside, and then come to the realization if this is a good approach to use or not. That would be my suggestion. Because in the UK, I mean, initially it was a very big area of research, but now it's kind of dropped off because people have realized that this may not be the best way to recycle the plastic. There may be better ways for us. My last suggestion with plastics is that now that I'm also looking into this, is that we should think about other ways to kind of recycle the plastic in pavement, not simply just kind of mix it with bitumen, or just put it in terms of our aggregate mix. Can we come up, can we make aggregates made of plastics? Can we encapsulate plastic? So you should come up with more creative ways. I think that would be my suggestion. Yeah.
Sir, the next question is one of the faculty join. He's asking like, sir, our student and can us join or use the machinery available over your station? Like here in IIT Bombay has allowed that facility to do this in virtual mode.
Yeah, absolutely. I mean, if you have, if you're interested to collaborate, or please feel free to reach out. I'm happy to have a chat with you, and then we can discuss. I mean, yeah, I think I already have a few collaborators in India, and we work on different kinds of tests together. So I would be happy to talk to you. Yeah.
The one more question from this addition of the plastic itself. The plastic waste being added in pavement increase aging, right, sir? And what amount of increase in rate?
So again, I mean, if you add the plastic in the bitumen, essentially you are creating a different kind of material. So when we talk about increasing the rate of aging, it may not be the aging that we think about in terms of oxidation. It may just be that its rate of stiffness has changed. So that's another thing. Yes. So when you add a X material to the bitumen, yes, you are increasing its maybe the rate of stiffening, but it doesn't mean that you're increasing its rate of oxidation. So you will have to benchmark it based on your on your modified material. I think to benchmark it in terms of bitumen without modification may not be the right approach. Yeah.
Sir, can you please name the methodology to effectively predict and mitigate the long-term effect?
Is it long-term effect of aging? Is it, or?
I think he must be saying about aging. So, like you have told us about this ozone technology,
Yeah,
oxidation.
yeah. Effectively predict and mitigate. So, I mean, in terms of prediction, yeah, you can use some kind of the traditional method is to use the PAV aging, which is the pressurized aging vessel. That way, you can predict how aging happens. That is the traditional approach. Mitigate, yeah, I mean, we still don't know. I think this is an area of active research. I shared some work about how we use the zinc-based antioxidant, but I think there are other antioxidants. So if there is any kind of students who are interested to work in this area, this is a very good area and upcoming area of research, looking at the aging retardant technologies. Can we look at other additives, maybe cheaper additives, safer additives that we can add to our materials to reduce the rate of oxidation? Because as I talked to you in the presentation, the approach that we're taking as a global community now to in payments is that we're looking at life extension more than recycling, because extending the service life of our assets, it is the most resilient as well as a sustainable approach. So I hope, if there are students listening today, you would take that on board. Is that when we think about sustainability, the most sustainable approach to our assets, it could be any infrastructure asset, is to make it last longer. So that's the key idea, I think.
Next question is, what are the unknown challenges in future you might think will encounter in this use?
Yeah, I think, see, so I talked a little bit about antioxidant, I talked a little bit about plastic. So there are actually many unknown things that we have not looked at as a community. So, for example, there is, now there's research looking at when we add these plastic materials into the roads, right? Is it actually really a safe way? Is it a safe way to dispose the plastic? Is there things like, microplastic that has been leached? Is it safe for the environment? Also, when we mix these plastics, antioxidants, during the mix process, right? Is this safe for the workers? So these are all things that we will have to think about in the future. Also, when we talk about the multiple recycling, when you recycle again and again, are these environmentally friendly? So I think two main things we need to think about is that are the processes that we are considering now in terms of modification, in terms of all of that, is it safe? And the second thing we need to think about is the life cycle analysis. So we say that using the plastic is more sustainable, but is it really more sustainable? Maybe the better way to use the plastic is to come up with some other ways to recycle it. So yeah, I think the two main areas that are good areas of research is, yeah, in terms of the life cycle analysis of all these new processes, and the other thing is to look at the safety. Is it, are our processes really environmentally safe? Yeah.
Yes, sir. In one of the research recently posted, I saw on the LinkedIn that these microplastic have been found in the very depth of the sea, and the people are
Exactly.
started saying like you are using the plastic in the road pavement, and because of the abrasion, it comes into the air and then cloud and
Yes,
then to
yes,
the sea. So,
yes.
sir,
Very
move
good.
on to our next question, sir. Uh, so please tell us about one chemical that can be, or the material which can be used as a filler and oxidant while job mixing for flexible pavement.
So, I mean, there's no one additive. I mean, it's still an area of research. I think there are a couple of them that
I
are
think so.
quite
I want to add
promising.
this to this question, sir. I think the filler basically they use are very fine sands, and during this
Yeah.
job mix, so I think he might be asking for some chemical to be used in the filler, like lime or something, to be work as.
Yes. Yeah, I think lime is a great one to start. I mean, there's still a lot of area. I mean, people are really interested. Also in the UK now, there's a lot of interest in lime. Another one that I'm quite interested is lignin. So I'm doing a lot of some research now regarding lignin. So lignin is basically it's a wood-based additive. It will be a filler when we add it into the bituminous mix. So I think, yeah, lignin is a very uh, good additive to look at. I think it is quite promising. I think there's a lot of work around the world. In the Netherlands, there was a big project on using the lignin because it's a waste material coming from the wood. So, and I'm sure in India as well, there would be some. I think already some of the organizations in India, like the CRRI, I think they're looking at lignin. So that may be a good area. Yeah.
Sir, the next question is uh, what's the best size of plastics? I think plastic to use. I mean to say
Right.
like
So yeah. So for the
while
plastics,
doing
I
the
think there's
shredding
two.
parts, that cutting part. So what type of the best
Yeah.
size, sir,
So
should we
there's
use?
two ways you can use the plastic. One is the wet mixing. Wet mixing is where you modify the bitumen. In terms of there, you don't need to consider the size because you want the plastic to melt. So right, you're making a bitumen modified bitumen. But when we're talking about, you're probably talking about the dry mixing where we add the plastic into the aggregates. So I think the best size seems to be the very small size. So in terms of you want the pellets that are kind of make your like really fine aggregate.
Like a powder, sir.
Yes, or slightly bigger than powders. That seems to be the best. But again, it is a very. I think there's another key point I think I didn't mention is that we recently did some study. We just looked at just LDP alone, which is a low density polyethylene, and we could see that even having the different sources of LDPE, we were getting completely different properties in terms of the mix. So those are, I think, the real things to think about. Can we control the quality of the plastic? Can do we know what exactly the plastic that we're looking at? So there are many variabilities I think that we have to control when using something like the waste plastic. So I'm not convinced that this may be the best approach. But I think, yeah, again, there are many years of research ahead. I think, yeah.
So we come to the last question, sir. I think this question will keep you in the mentor position, and it is from your last slide. Someone is writing how to write the PhD application. I think basically for your college, and even for the faculties. So most of the participants are the faculties from very different colleges of the India. Around 30 plus colleges faculties are there. So I think the question should be extended to post PhD, postdoc, for the postdoc also. So sir, how one can get the help, and what are the chances, and what should be in what manner it should be written so that the application gets accepted, sir?
Right. So, firstly, coming to the PhD, yeah, I mean, for the PhD, if you're interested to apply for a PhD, I think the first step would be to send either me or the other two academics that you saw in the slide. Just send us an email, just expressing your interest and with your CV and so on. And the next step would be to apply through the university system. But again, the decision is mainly dependent on us. Obviously, if you have talked to us before and we think you're a suitable candidate, your application will be accepted. And the third step, which is probably the most important step, is the funding. So the funding is basically, it's a competitive funding. So if you have a very good profile and you have a high score in your masters or undergraduate, then yeah, then you can apply for the funding. And yeah, I mean, and then you might be accepted. So I have a student from India as well. She started recently, so she got the faculty funding. So it's not impossible or something. It just depends on your results. The other opportunity is to apply for other kind of competitive kind of fellowships. The second question in terms of the postdoctoral is that, yeah, so I think there's two main opportunities for postdoctoral fellowships. One is, yeah, we often have like different kind of advertisement. This is based on our projects. So currently we just closed one advertisement for the postdoc. So for that, you just apply when you see it. The second option is, through there are different kinds of fellowships that are offered either from the Royal Society, from the Marie Curie Actions, and so on. So, again, you approach us and you tell us if you're interested to apply for it, and then we can support you to write an application. And then if you're successful with that, then you can, do your postdoc. The other option is, you also have the visiting faculty. So previously there was a colleague of mine now who's back in IIT, one of the IITs. He visited us as a visiting scholar. So I think the Indian government provides some kind of scholarship to visit foreign laboratories for 1 year, I think. So those are I think the three main opportunities. But if you're interested to know more, or yeah, you just want to collaborate, you just feel free to write to me. I'm very open to discussing with people from India and so on. So yeah, please don't hesitate. I'm happy to talk to anyone. Yeah.
Thank you, sir. We especially appreciate your insights on all the topics you have shared today, sir, into the challenges and the opportunities associated with the developing sustainable payment materials, sir. Your emphasis on incorporating data science, sensor technology for design, health monitoring highlight the innovative approaches that are shaping the future of this field, sir. Your international experience and expertise gained from your work at the prestigious institute like Nottingham, Cambridge, Texas, at University of Texas at Austin, have enriched our understanding of the global perspective in the pavement engineering. Thank you for sharing your passion for this field, and for inspiring us to think critically about how we can contribute to creating a more sustainable and efficient transportation infrastructure for future generation. Sir, your presentation has been a valuable addition to our FDP. Thank you, sir. Thank you so much, sir. This one is the
Thank you.
very last session we have in the FDP. So, sir, thank you for making it so much memorable. Thank you, sir.
Thank you, everybody. Thank you for your time. And yeah, sorry to keep you so late. I think it's already quite late in
No, sir,
India.
we
So enjoy
normally,
the rest.
for the weekdays, we have a timing for 6 to 9 p.m. For
Okay.
Saturday, we have to bind it up by 8 a.m. because now there will be an exam session, the feedback session, and the validity session. So after
Okay.
that, we
Yeah.
will be concluding this FDP. Thank you, sir. Thank you for joining us, sir.
Thank you. Bye
Thank you.
bye. Yeah.
So everyone, we are having 13 session 13 feedback attendance in the chat box. So, as posted, we will be having the validatory session at 7:30. Meanwhile, let me check that all the attendance have updated or not, and the questions available on the web portal or not. So, just let me check it first, and then I will post all the details on the WhatsApp. Thank you.